This is our car setup. Right here we have the ultrasonic sensor. It sends out an ultrasonic wave and then it bounces back into this one, and it takes the time that it took for the ultrasonic wave to get back to calculate the distance. These are our 4 transistors. They control the flow of electricity into our 4 motors for the wheels. This is our power supply, just a 9-volt battery. And this custom circuit board shield just connects to the Arduino board, where it has the code and programming onto it.
So once we had our little cart set up and ready to go, we needed to get a model of how it behaves so we could tune our controller to the model and be able to test and make sure it would work correctly. So to do that, we needed to figure out how fast it would go with different powers to the motor. So we set a time. We said we're going to let it run for 2 seconds at various powers. This voltage bit, that is essentially percentage times 255. 255 volts would open our transistors all the way. So that's what this is. Distance in inches, of course, how fast it got. And from that, we were able to get the velocity over those 2 seconds. Once we plotted the points, we got a nice little graph that looks like this here. As you can see, if I move it up a little bit, as a linear portion between about 40 voltage bit and 100 voltage bit, and then after that it kind of smooths off and as the motors max out their power. After lower than 40 voltage bit, our cart refused to move. It didn't move at all. So we use this to create a model that we could later use that gives us, based on the power it's receiving, how fast it will go. We also made this here. This is a correlation across the linear portion. It essentially works like an FOPDT model and gives us this nice gain for velocity based on the power sent to the motor that we will use later. So then we set up a model in Python that uses that equation that we had to get a velocity and then integrates that to show position. This shows out a test function. Then we installed our controller into it. When we installed our controller, we made sure that if we fed less than 40 voltage bit to it, that our speed would end up being 0, as you can see there. And then we modeled it with a gain parameter for our P-only controller, as it's an integrating system. And you can see the response position versus time here with different position set point changes. And you can see here the error. This red bar represents a 0 error, so you can see it overshoots just a tiny bit. But overall, this gave us the best combination of speed versus control versus not overshooting and hitting what we're trying to follow. And you can see when we put this controller into the cart, it behaved very well. Right there.
Yeah, well, it's 30% of my grade, so I need to get
Yeah. Doing set point tracking and having our car follow this cardboard.